I'm Farhad Fallah from Aldec company. In this video, I'm going to show you how to run user-guided multi-FPGA partitioning using Aldec's HES DVM on the AWS cloud. In the previous video, I explained how to run automatic partitioning using HES DVM. However, some projects may require some manual customizations and user needs to have more in-depth access to features such as moving instances, cloning them between partitions, and assess the results at the end. Let's have a deep dive into the HES DVM's advanced partitioning features together. So before reaching to the Partitioning tab, we need to run compilation, synthesis, and adding the design to HES board, which I've already covered in another video called How to Use HES DVM on the AWS Cloud for Multi-FPGA Design Partitioning and Prototyping. You can click on the link in the video to watch that one before going through the partitioning. Inside the Partitioning tab, we see two boxes. The first box here shows the FPGAs, so we can assign the FPGAs to each partition in this box, and then we see the resources associated to that FPGA and also the partition, name of the partition right here. This box here, we see the resources that we have. We get the designs hierarchy, and then also the ports, and then the name of the partitions that's going to be mentioned right here. So here, as we see under the design window, we get the design hierarchy, and as we add more partitions to our design projects, we're going to get more columns right here. Under the resources, I can see the number of lookup tables, number of flip-flops, memory, and DSP blocks. As I see right here, it says 233.9%, and I can see under the design that if it's an absolute value or percentage, by choosing this option right here, I can change it to absolute, and then I can make it percentage. So I stay with percentage, and it shows me that it's a lot more than 100%. Usually only 90% of FPGA resources should be filled, and here we have 233%, which means that we need to divide this design into multiple FPGAs. There are some options right here that I can choose from. For example, this one, as I mentioned, is percentage or absolute values. If I want to, for example, disable this column, I can just say, okay, in my design, DSP blocks are not that much. It's only 1.4%, so I don't really care about it. So I can just disable, and then it goes away. So I get narrower columns here with less information, which is going to be more neat to continue. So same thing with other columns, for example, memory, if I want to remove it, or flip-flops, and then I have options for lookup tables as well. One more thing I want to mention here is creating new partitions. So as you see here, the resources already, they're like very high. We need to keep it less than 90%. So I can go over the design hierarchy and open it, open the top module, and see what do I have here and how are the resources divided between different modules. So for example, I can see the decoder that I have, it's basically getting 75.9% of the design. So what I can do, I can just send this to a new partition. To do that, I just right click and then go to move to partition, new partition, and then I call it P1. Once it's done, I can see all the resources are moved to P1 partition. So the 75.9% of here lookup tables are moved to P1, and I can see the swerve right here, it's deducted from whatever it was before. 75.9% is deducted from it, so it's right now is 150%. And we see one T right here. This T, if I just hover on this, it says that T means instance is top in partition. So we can see a T and a little arrow which is pointing downward. It means that we can go down, down, down to find the instance that is moved to this partition. Here we moved decoder, DEC instance to partition 1, so T is right here. But if we're gonna navigate through the design, this arrow right here and the T is gonna show us what it was moved to P1. So if I wanna move it back to P0 to just show you that this value right here 150 is gonna increase again, so we can just go to decoder and then move partition to P0. So we move it back and see here the P0 value for lookup tables and also flip-flops are changed and are increased. So I again move this to new partition P1. So far we have two partitions, P0 and P1. I'm going to create another partition and move this memory module to that. The new partition is called P2. So I created, and all the resources are in P2 partition now. Another very useful feature that DVM offers is cloning. By cloning, you can clone one IP or any module into any other partitions that you have. It comes very handy when you have a module or an IP in your design which is heavily connected to other modules or IPs in your design. So what happens if you put it in one partition, it's gonna consume a lot of physical IOs on the board to route to other partitions that you have. Instead of that, you can clone this module into each and every other partitions that you have, which saves you a lot of physical IOs and also time for routing this. Another common use case of cloning is to reduce board level routing of design internal clocks and resets. Designs usually use a few external clocks to generate tens of or hundreds of gated or divided internal clocks. For example, in my design, I have design ports. There are some clocks, external clocks that are coming to my design. You can use cloning feature to replicate such clocking modules in all partitions to avoid routing internal clocks via FPGA to FPGA I/O connections. It really improves connectivity and timing. For example, in my design, I'm going to clone this DBG module into partition P1 and see what happens. So as you see, the resources here is still the same, and we have the same resources under P1 partition. C tells us which one is which instance is exactly cloned, so we can find out by C. Okay, DBG is cloned here, and tip is the top, as we explained before. So if I follow the arrow, I can see that okay, this one is the top module that is cloned, and then this one is also the top module that we moved it here. So far we have 3 partitions, and we tried to do cloning for DBG into partition 1. And so imagine we have a very huge ASIC designs, and we're gonna get a lot of instances as modules for this design, and to do the partitioning at the end of the day, we're gonna have many T's and C's in each partition. So if we move multiple instances into one partition, we're gonna have multiple T's, and if we clone them as well. So how can we navigate through and find the top level and the cloned partition, the cloned instance? So to do that, DVM provides a very nice filtering option here. So to find only the top level and also clone modules, I can just select this T over C, and it automatically shows me only T's and C's for my design. So I can deselect this and get back to normal. Another nice filtering feature is filtering based on the instance name or the module name. So we have modules and instances here, and if the design is very large, we're gonna get a lot of instances under the design box. And instead of navigating through each one to find out the instance name and if you want to get any information from the resources it's using or any other thing, instead of that we can just filter using instance name or the module's name. I just click here. Now I'm going to find, for example, instances which has the name trigger. So it's going to show me all the instances that contain the name trigger in them. And I can deselect this again, like T/C that we did. Also we can filter using case sensitive option or the regular expressions that we have, as I mentioned, based on the instance name. Another nice feature that we get in this window is drag and drop. So if I wanna reorder the partitions column, so I can just drag one and drop it. And as you see on this window also, where we assign FPGAs, the ordering gets changed too. So if I try to put P2 here, and I can put P1 back to normal, you see all here also the ordering gets changed. One more feature that we give is to sort each column under the resources, either ascending or descending way. So if I change this right now, you see this is now sorted as a descending way. It goes all the way down to the lower numbers. So I can do this for any resources that I want, and it gets changed. There's also one column for the ports. This shows me the number of module ports that I have. So if I hover on any number, it tells me exactly how many input and outputs are incoming and going out of that specific modules. HES DVM separates design ports in another tab. So if I open it, I can see the inputs and outputs from my IP. So under this, I can see the global level signals. So for example, I have JTAG signals coming to my design and going out of my design. So the actual JTAG connector, let's say, is connected to FPGA 2, where eventually P1 is going to be connected to that, the partition 1. So in that case, I have to move all of the signals related to JTAG to partition 1. To do that, I just select all the JTAG signals and try to move them to P1, where the actual JTAG connector on the board is located. So we move them here, but what we see, there are a couple of new symbols right here. One of them is a check mark. The check mark tells me where the actual signal is located. The actual port or signal is located. And the D tells me where the driver for that signal is located. So once I move them here, all the JTAGs, I can see that the driver for the output, JTAG TDO, is still under P0, but the actual port is moved to P1. And then for rest of them, because they are input, the driver is also moved to P1. HES DVM also enables us to assign global signals. On any prototyping board, FPGA prototyping board, we have some global signals which are routed throughout the board, and they are connected to each and every FPGAs on the board. Usually we can use clock signals, especially the core clock, which needs to be connected to all the FPGAs or all the partitions. We can use that as a global signals. To define that, we right click and go to connect to global signals. So on my board, I have these signals defined as the global signals. So I can choose one of them. I choose the first one. And this G shows up here, which means it's a global signal in my design. Another useful data that we get from this table is the number of fanouts that each signal drives. For example, here we see the core clock drives 1201 signals under partition 0, 228 signals under partition 1, and 46 signals under partition 2. So far we covered many detailed features in this window. Let's go to the top window and see what information we get here. We get the partition's name, and we have P0, P1, P2 right here, and then we get the numbers for the interfaces between each partitions. For example, here I see P0 to P1 we have 2532 connections, and also I can see from P1 to P2 there is only 47 connections. And also on the left side I get the resources for each partitions, and then here I can assign FPGAs to each partitions that we have. We have P0, P1, P2, so I'm going to assign it like in the same way. I go to select FPGA, assign FPGA 1 to this one, and then I'm gonna assign FPGA 2 to partition 1 and FPGA 3 to partition 2. So this FPGA assigning can be also done automatically by going through partitioning and run autoplacer. After doing that, we see a couple of numbers showing up. For example, L over P ratio, which is the number of actual physical IOs on the board, and between this P1 and P0, and then the number of logical connections which we have in our design. This ratio is better to be as close as possible to 1 or under 1, and anything above 1 means that we need to do multiplexing, and the number of logical connections that we get is much more than the physical connections. For example, here we have like 7 times more than what we have on the board, so we need to do multiplexing here. And for example, and here between FPGA 3 and FPGA 1, we see that it says not a number because there is no connections between these between these two FPGAs on the prototyping board that we have. To keep this number as low as possible, one of the ways is to do the multiplexing, and the other way that we can do is to move each instance to different partitions and see if we can lower this number. For example, right now we have 7.2 and we have 2532 interfaces between this P1 and P0. We need to move some modules around and see if we can lower this number, or any number here that there is no connections, the actual connections between the FPGAs. To do that, HES DVM provides an impact analysis tool. What is impact analysis tool exactly? So if I want to see what would be the results of moving this module into each and every partition and try to compare them and see the results, or see if we can lower this number right here that we get 7.2 L over P, impact analysis tool comes very handy. I can just right click and just choose try to move to partition. So I can do this with RV top, or I can just open RV top and see what else we have underneath of that to move. So here what I see, for example, this ISU is using like 59% of the lookup tables, so I can try to move this. I can choose either each partition or partition 1 or partition 2. I try to move it to each partition to see the results right there. So if I expand this window a little bit so I can get more information. So DVM creates two more tables for us. One of them says, what if we move that instance to partition 1, and how about moving it to partition 2? So we get different numbers here. For example, L over P, that was very important to us. If I check it, so if I move that module into P1, the number reduces a little bit, but if I move it to P2, that goes like almost to 5.8, which is an improvement for us. So it's a little bit hard to follow the numbers and see which one is improving, which one is not improving. So to make it easier, DVM provides one feature here. So if I select it, I can see by arrows what happens exactly in each interface. So the green color tells me that we are getting better, or we are reducing the connections that we have between those two partitions, and the red sign tells me no, the number of connections interfaces is going high. Based on my table, I can see if I move that module into P2, I get a better result. So I'm going to remove the other table. And here, I'm going to accept this, and I want to have this instance into P2. So I click on this check mark. So this is done for me, and if I expand this, it was too much. So I can see the instance that I transferred, which was ISU, into under the P2. In this table, we can see some exclamation sign next to different numbers that we have here. So if I hover on that, it says no physical connections between selected FPGAs. So this means between FPGA 1 and FPGA 3, where the partition 2 is located, there is no physical connections, actual physical connections on the board. But there is connection between FPGA 1 to FPGA 2, and from FPGA to FPGA 3. So here, to make these connections, we need to route signals interfaces from FPGA 1 to FPGA 3. So FPGA 2 here plays a role like a bridge, or we call it feed through FPGA, and gets the signals from FPGA 1 and connects them to FPGA 3. To define this bridge, we need to just open partition 0. So I'm going to expand this table. So we see the signals, and I can select the signals that needs to be rerouted through the third FPGAs. For example, I'm going to select these signals. So if I right click and then set route, here tells me signals are going out from P0. This is a sign for it, and they are going inside partition 2. And I can select the FPGAs, the partition or the FPGA that I'm going to use as a bridge here. So I select P1, I transfer it as a bridge partition, and I click on OK. So I can see the B sign, which means bridge, here under the partition 1, which is connected to FPGA 2. So this means that FPGA 2 is used as a bridge between FPGA 1 and FPGA 3. So there are many signals in my designs which need to be rerouted through FPGA 2. I can do this manually as I showed you, or I can use an automatic feature by DVM to just do it automatically. So I can click on Run Auto Router. Once it's done, I can see that some FPGAs are used as a bridge, but HES DVM found that there is a fourth FPGAs on the prototyping board, so we were using only 3 of them. So this is a better way to use the fourth FPGA for this routing and also partitioning. So as auto partitioning is much more smarter than manual in many ways. So HES DVM did this for us, and which is very helpful, and we can see that even the numbers L over P's are lower than before that we had. I'm going to expand this window back to the normal, and we don't see any exclamation sign as we had before. Now we have all of our partitions ready, and we can go to the next step, which is about connections, but this is going to be covered in another video. In this video, the main point was to talk about the details about partitioning features that we have in HES DVM. So to wrap up this video, I just go through what we've done so far briefly. So we added the design files to HES DVM, and we ran the compilation and elaborations and synthesis. We added the design to HES board, and under the clocks tab, we ran the clock conversions. Under the partitionings, I explained features about each window, what are the detailed features that we get, and also we went through the impact analysis tool that DVM provides, and I talked about the bridge connections if we don't have any actual interface between 2 FPGAs, so we use a third FPGA to pass through the signals. And at the end, we use the auto router features to route the signals between FPGAs. I hope you liked this video, and just if you have any questions, please visit our website at www.aldec.com. Thank you.